Yeah, from Salerno. Okay. Yeah. First of all, thanks the organizer to allow me to be here to speak about my work. Yes, I come from Salerno. It's a city close to Naples. And thanks to take part to this conference. Unfortunately, with respect to the topic of the conference, this work maybe is a bit far. The point of contact is with superconductivity, for sure. I will speak about Josephson junction, about a specific kind of Josephson junction. This work is done in collaboration with Roberta and also with Francesco Giazzotto, that unfortunately is not here. Also with Alessandro Braggio, Paolo Salinas, and Giampiero Pepe of the Naples University. But moves to the focus of the talk. Okay, I'm sure yesterday we heard a lot about Josephson junction, and I'm sure you know everything about conventional Josephson junction, the sinusoidal current phase relation, and even the possibility that at a temperature different than 0, you can have two kinds of transport, the Josephson and the quasi-particle transport. But what's happened in the case in which the system is asymmetric, in the sense that the superconductors that form the junction are different, and even the temperature that form the junction, at which the electrode reside are different. There is a thermal bias in the system. I will try to show you some results in this direction, looking at both the Josephson transport, the Josephson current. In particular, we focused on the critical current in the system, and the quasi-particle transport. So step by step. First of all, the Kfar pair transport. So the Josephson component. The results I'm going to show you are contained in these three papers. At the end of the story, what we did was to study this equation. This is the critical current for a system that can be exactly formed by two different superconductors that we assume at different temperatures. And trust me, in a system which is formed by same superconductor and at the same temperature, this equation becomes the well-known Amberger-Bartov relation that maybe you know. So what's happened to this system? First of all, define some parameter, the asymmetry parameter that here I have. The asymmetry parameter, which is we are assuming BCS superconductor. So at the end of the story is simply the ratio between the critical temperature of the system. So let's start from the case of a symmetric system. So R is equal to 1. In this case, we have a critical current that resembles the Amberger-Bartov that monotonically reduce by increasing the temperature. We are assuming to change both temperature T1 and T2, to left and to right. But when we change the asymmetry parameter, that is, we are unbalancing the two critical temperatures, something of peculiar occurs. In fact, you can see that, for instance, starting from the case in which R is less than 1, we have a jump here at the temperature, very high temperature, we can say. A jump in which the critical current reduces. In the opposite case, in which the asymmetry parameter is larger than 1, we have a very peculiar situation in which at least one curve around 1, in which the critical current increase by increasing the temperature. This is quite strange situation. The position of this jump can be inferred that by considering is due to the alignment of the singularity of the anomalous Green function that enters in play in the expression of the critical current. And at the end of the story is when the gap are equal. So this means that looking at this graph, for instance, in a case in which R is larger than 1, the window of temperature at which this condition is fulfilled is close to the critical temperature. So it's quite high temperature. But of course, it depends on the asymmetry of the two systems. So, well, starting from this case, focusing on one of these curves, of course, first of all, this is a theoretical analysis. There is no, up to now, an experimental evidence of this kind of behavior. We are trying to do some experiment, but we have no, still we have no these results. So one thing that we proposed was a single photon detector. So, we managed to set the temperature of the system a bit below the temperature at which the critical current jump, and imagine some situation in which the absorption of a photon can get the temperature of this lead to increase a bit, and to record the absorption of a photon, to read the absorption of a photon as a critical current increase. In particular, here there is a simulation of, we consider the system a bit more complicated because we included all the channels, all the thermal channels in the system. So this is the thermal balance equation for the system. And in the case of the absorption of two different photons, so the temperature increase and the critical current of this system has this rectangular-like envelope, and the width of these rectangular pulses of critical current, we can say, give us information on the frequency of the absorbed photon. So we were able to define the sensitivity of this kind of device. This is a proposal, maybe a bit speculative, of course, but starting from this, the problem of this is that we have to carefully set, and it's also the problem of the experimental realization. Okay, we have to set carefully the temperature of at which the leads of the system resides. So to overcome this problem, we thought to another configuration in which we have a tunnel junction between two proximized leads, in the middle of two proximized leads. Each of these leads of this wire was enclosed in a superconducting loop. In this way, the gap is controllable by the external fluxes. So at the end of the story, we still need the presence of a thermal bias, but we don't need the fine control of it. And we can address the fine control with the fluxes, with the external fluxes. We are thinking the possibility to excite the two rings by independent coils in this case. So at the end of the story, in this plot, we have the change in brightness of the density plot reveals the presence of the jump that I showed you before. The point here is that with this configuration, still with some thermal bias, but even in the case of a symmetric device, we can have this observe this kind of critical current jump. And even in this case, we can define a figure of merit, and we can study how the figure of merit, this figure of merit, which is the flux to current transfer function for this system behaves, and we can search the optimal working point, we can say. And this is, again, another theoretical proposal, for sure. And this concludes, I can say, the part about the Kuiper-Perry transport. And we looked also at the quasi-particle transport. This is another part of the story. Yeah.
Before you go ahead.
Yeah. Because
I understand it comes out of the integral, but what's the intuition? What's going on at that?
The sort.
You explained it and I missed it. I'm sorry.
No. In the time that I had, no, I didn't. I mean, in such a way, hoping that at the end of the story, this kind of behavior will emerge really in an experiment, real experiment. The system chooses one of two solutions, we can say. And the jump is, because each jump resembles a single Amberg or a Baratov relation, and the system at a certain point jump in the other, or maybe took this other jump. Is a play, yeah, is this at the end. Can I go forward? Yeah, maybe we can speak again about this. No, this other part, this is really another story, because at the end we studied these results are contained in these two work of Francesco Giazzotto's group. First the theoretical prediction, and then also the experimental works confirming this phenomenon. What they did was the same, but studying the quasi-particle component and suppressing the Josephson component. So they constructed the specific, they used a specific geometry to suppress the Josephson component. In this case, what they observed was a thermoelectric effect. So I want to spend a couple of words about the thermoelectricity, because they observed a nonlinear, very peculiar nonlinear thermoelectric effect. So thermoelectricity is we can say, is a universal property of substance that at nanoscale we can manage to study with this scattering approach, a very generic scattering approach, a well-known scattering approach. In the linear response regime, is very well explained in this review, there is no chance. I mean, when the system is a particle symmetric, we have no possibility of thermoelectricity. In particular, in a tunneling junction, where the density of states are symmetrical, particle or symmetric, at the end we have no thermoelectricity. But if we go beyond, so if we touch the full nonlinearity of the problem, by simple consideration, by hands we can say, the two energy, again, in the semiconductor model for tunneling, which is well used, often used in the system, here is presented both the electrical and the thermal component of the transport. The energy, the two law, thermodynamic law, say us immediately that at the equilibrium the system have to be dissipative, no chance. Instead, if we unbalance, if the systems, the temperatures are different, for some combination there could be the possibility to have some system which is reactive. I mean, in which we can have thermoelectricity. And this is exactly the case. Another signature of this is the appearance of what is called absolute negative conductance that I'm going to show you. So enters in detailing in our system, that equation. I want to focus on the two parts. This is not, what I'm going to tell you is not the full story. It's only to show you that there is an asymmetry. So I want to focus on the density of states. These are two density of states that in the case of a symmetric system, you can see that here, the part that I use here, this 0 and this 0 are the same. I mean, at the end of the story, when I do the integral, the sign are given by the other terms. I get 0. There is no possibility to have something which is not 0. Instead, if I move in a situation in which the gap are different, look, this side is larger than the other one, here we can have some asymmetry in the description, we can say. The green part giving a 0 when you multiply the two sides, the two density of state is larger than the yellow one. In this case, we can have some situation in which at the end we have thermoelectricity. These are theoretical curves. In particular, the red one is a case in which we have thermoelectricity. Here we have the product high V in this part is negative. In particular, we have a linear unbiased thermoelectricity, small voltages, but 3 minutes. Yes, I think I'm up. And also there is a peak. This peak can be obtained with this very simple plot. This is the case in which the peak dose coincides. So very rapidly, these are another collection of theoretical plots in which looking the curves, we have two Seebeck voltages, and even the appearance of absolutely negative conductance, that is, the slope is negative at 0. This effect was confirmed experimentally. So, going fast in the experiment, because also the experiment was done by the Josephson group, I'm not involved, sincerely. So, they used this kind of configuration, and what they observed was exactly the formation of this kind. The dashed black curve is the theoretical one, the other one are experimental curves. They observed exactly the emergence of this phenomenon, the thermoelectric effect with the Seebeck voltages. And they proposed also a sort of thermoelectric engine, Josephson engine, attaching a resistive load. And in this way, they was able to characterize an hysteretic voltage profile, bipolar voltage profile. Starting from this, with Roberta, we thought, okay, in this case, we have to break in such a way the particle symmetry. Can we start with a system which is intrinsically particle asymmetric? Specifically, we studied a case in which we have a junction in which one side is an iron-based. There are a lot of examples of junction, not so good quality junction, honestly, but made in this way. Without entering the detail of the model, it's a very minimal model. Starting from these, there are a lot of works in which they improved the model. This is good for describe the pnictids. So starting from these and looking at the density of states, it's quite clear that the electron-like part is totally different with respect to the whole-like band. The system is particle asymmetric, intrinsically particle asymmetric. This case, the dose is gapped. So we studied we decided to study first this kind of junction, iron-based attached to a normal. And in this case, we studied the linear unbiased thermoelectricity. These coefficients, the conductances, give us information and us information that are useful for the experimentalist. And we obtained, in the first case, spanning the various parameters, a zeta t, which is often used by experimentalists, quite high zeta t, a value larger than 1 are good. But considering a system with a superconductor, we obtained a situation in which, for a specific combination of the various parameters of the system, I have no time to describe in detail, but we obtained a value of zeta t very large. The value 40 is a very large. Speaking with our colleague, a value of 3 was a good value for experimentally. This is, of course, a theoretical work, so we don't know. But 40 was really is really a good result. So that's all. This is briefly. I tried to convince that in the case in which you have a Josephson junction, you unbalance both the gap, the critical temperature of the system, and the temperature at which the system resides, something of peculiar can happen. And here there are some examples. That's all. Thank you.